everybody. Welcome, welcome.
They're also lower.
Okay, few quick things, then we're going to jump into our lesson today. So first thing is, I don't have your FRQs for you. You'll have to wait till Monday, and then I'll get it to you. Okay, sorry to make you wait. If you want to get started on the multiple choice corrections, obviously you can. I won't set the deadline, though, until I get you your FRQs back. So the deadline starts 2 weeks from when you get your scores back. But I'm not going to count Thanksgiving as part of that 2 weeks. Because that's, I don't want you to have to do anything over Thanksgiving besides have a good break. Okay? Where we're at and where we're going for the rest of the term, everybody. Give me attention here. So we're starting Unit 4 today. I did this last year and it worked really well, so we're going to do it again. Unit 4 and Unit 5, we're going to combine into a single test. They're both shorter units, and by doing that, that gives us one whole other day for learning versus having to have 2 separate test days. So Unit 4 will be pretty short, but then we'll roll straight into Unit 5, and then we'll take the test for both of them on the 19th of December, which is the second to last time I see you before the end of the term. So a few things to keep in mind. Number one, if you're headed off on Christmas break early, I highly recommend you talk to me and we take the test before. Because the last thing you want to do is have to think about it over the break. Okay, and even if you're like, oh, I'll study more, no, you won't. Okay, just take the test before. Okay, second thing is the test for these units is going to go on next term's grade because we're taking it right at the end. All the homework and quizzes will still go on this term though, so kind of keep that in mind. But the test itself obviously will go on next term because you won't get it back till right before the term ends. Okay? I think that's all I was going to say. Okay, first thing we're going to do to start off today is there's kind of 2 objectives. I wrote the main one, but we're going to start by talking a little bit about chemical and physical changes, which is something that I'm assuming you all have learned to some extent, right? Even I have a sister who teaches elementary school, and even elementary school they introduced the idea of chemical versus physical change. But it's still something we want to make sure we have a really sound understanding of what does it mean, particularly from all 3 sides of our triangle. So that's what our boxes here are talking about, is with a physical change, what do we see with our eyes? What can't we see, meaning at the molecular level, and then symbolically, how does it change? Zach?
What happens to the board? Showing where diamonds were.
Oh, sorry. Took them away for the moment. They will come back one day. Oh, sorry. No, you're good. Anyone else miss getting them? Okay. Another thing I forgot to say, one thing with the setup here, and then we'll jump into this. So the note packet looks bigger than it is because it's single-sided is how it's printed. That was actually on purpose. The reason being is I've talked about it before of using colors to help in your note-taking so that you see the pathway that you've got there, right? Rather than just seeing your notes as, here's what I did, the colors can indicate to you, here was step 1, here was step 2. It can highlight and bring things together. So I think there's a lot of value in that. So I want to encourage that of you, which is number one, why I bought all these highlighters and they're in the box. So these highlighters and pens are for your use. There will be times where I tell you to use them, but feel free to use them whenever during the notes. But I found out that they bleed through paper more than I thought highlighters should. So that's why I printed it single-sided, because I would not be able to take notes with something that bled through and then right on the other side. It just would drive me crazy. So I didn't want to drive you crazy as well. The other thing I just want to say that I didn't say last time because of our test, I got some new periodic tables if you haven't noticed. They're updated now in terms of some of the elements weren't even on there because they were out of date. So now we've given OG its proper spot on its periodic table. I also added, because I am slightly OCD, there's magnets on them and there's magnets on the table. If we could just get in the habit of before you stack your chair, put it in its spot and then stack your chair. Every day at lunch I have to go around and fix everything because I just can't handle it. But it would save me so much time if I wasn't doing that constantly. So, okay, here's what I want you to do, okay? I'm going to show you 3 demonstrations. These 3 demonstrations are all physical changes, okay? First step is just silent, so no talking, just observe, and think about these 3 things, though. So as you're observing, you're thinking about, okay, what do I see? What can't I see, meaning molecular level, and then what symbolically is going on? Okay? After I do the 3 demos, then I'll give you a few minutes to talk as a group, and you'll see what you can come up with. Okay? Keep in mind, don't be specific to the demos you're seeing. Okay? Like, I don't want you to write what you saw in the boxes. Think of, I want to write down something that can apply to any physical change. Like, this is true for any physical change, no matter what it is. Okay? Then we'll do the same thing with 3 chemical changes to compare and contrast. Okay? All right, so first step, 3 demos, just observe. Okay, the first one I'm going to show you. All ready? I have some aluminum foil. Demo number 1. Okay, that's one physical change. Physical change number 2, I have some water, salt. Okay. And physical change number 3, it's a little better. Sorry, I can't lift it that high. I'll hold it up. No. Okay. Boiling liquid nitrogen. No.
What if you breathe in a lot of it?
Oh, I remember that one on my hand. It's so weird.
Yeah, it was sick. You should dump some on me.
So it steams frozen. You could put marshmallows in it. I have it on our plan, but we do it after the AP test. We do it on a day where we make liquid nitrogen ice cream.
Wait, can you dump it on my head now?
Can you put a little bit on my hand?
Okay, 3 minutes. Those are your 3 demos. Talk with your table buddy. Share your thoughts. Fill in these boxes. What can we come up with? Ready, go.
We see physical change. What can't we see? Not physical change. What do you write? Physical change.
What does it mean? What do you write?
No. What do we see? We see things changing in some way.
Or not changing at all.
So crumpling aluminum foil, dissolving salt in water, boiling liquid nitrogen. But in general, what do you see with the physical change? What can't you see? What's happening at the molecular level? And then symbolically, what would be going on?
Or displacement. What do you write? What you can't see.
Alright, if you have it, you should be talking with your table, share ideas, add things that you know now. That would be like
Yeah. We can't really see what's happening down at the molecular level, but we can see that it's changing some way.
Oh, are we supposed to see? Are we supposed to write that? Microscopic molecular symbolic?
I don't know. Because you can only see macroscopic.
You can't see molecular. You write symbolic. Are you going to the football game tonight?
No, I've swum.
Alright, you got 10 seconds.
What?
Senior state. Come and get me missing swim.
You can miss
My
me.
coach would kill me.
I bet Amanda's skipping.
Lynn's not going to senior state.
Oh,
It's gonna be our new jam in here.
I bet you'll be fine.
Okay, Yes.
How many times in your life?
They're there.
This season, I
I
missed 4
just needed an extension
Actually, no.
for fall break.
because
So
the
it's
cord
gone.
wasn't long enough, and I don't want to run the lights down
I
the
don't miss
wall.
swimming.
I have my extension cord. I was gonna suggest saying,
Apparently, you do for
but I
football
can't reach that.
games.
I'm not swimming. I'm
Because I
not
used a ladder to
going
put the
to
lights
meet.
up.
Oh,
Then I took
okay.
it
You're going to the meet.
I'm going to meet.
I'm gonna go see if I can find a ladder during lunch.
I think I might be able to get one.
Because they've been there actually
Get
since
one
lunch.
what?
You want to fly?
Oh, yeah.
Okay,
Fly.
here's what we're gonna do next, everybody.
You got it.
We're not gonna talk about it yet. We're gonna go on to chemical change. So same thing, I'm gonna show you 3 demonstrations of a chemical reaction. Your job is to identify, what do I see with my eyes when a chemical change occurs? What can't I see but is going on at the molecular level? And then how would I write it, meaning symbolically, plus sign, arrows, what does it look like if it's a chemical change? Okay? Once again, don't write things that are super specific to just what you're seeing, but could it be applied to any type of chemical change? Like if I see this, I know it's a chemical change. Okay? All right. Freezing beaker here. I'm gonna help this go along faster. So it's still boiling. It's just cooled the beaker a ton, so it's not cooling as fast. It's not boiling as fast. So to speed it up, this is not a chemical change. It's just me speeding up the boiling. I'm gonna add some warm water
A catalyst.
to the beaker. You can think of it kind of like a catalyst. That way it just goes away faster. Okay, first demo. Oh, this. Okay. All right, I have some copper chloride. It's a 1 molar solution. What does it mean to be 1 molar?
1 mole.
1 mole per liter. Thanks, Caleb. That was my base for that. Right? So copper chloride is not a liquid. It's just been dissolved in water, right? Makes a pretty blue color because the compound itself is like bluish. Okay, I'm gonna pour some into our flask here. And then I'm gonna combine it with our aluminum foil from earlier. And then I'll bring it around as it, see what it does.
That's crazy. Whoa, dude.
Okay.
Whoa.
Dang. That's crazy. Is it gonna... Aluminum foil gas.
What's that?
Is that the gas is from the liquid, right?
It's not. It'll smell very familiar.
Is it
What
chlorine?
too? Oh, it's chlorine.
Oh, wait.
Okay, wait.
Yeah.
Oh, it does smell like chlorine. But not really strong.
Some people are more used to smelling chlorine than others. Okay. I'll let it keep going. By the way, I didn't say this. It gets very, very hot. That's why I'm holding it at the bottom. It's too hot for me to hold up top. So, a lot of heat. Okay, we'll let that sit there. Okay, number 2 chemical reaction. All right, I have some 0.1 molar solutions here. Okay, of potassium iodide and lead nitrate. Okay, so once again, they both look like water because the substance has dissolved in water. Okay, I'm just gonna pour these 2 things together. Okay, so I'm gonna load this one. So Ki, potassium iodide.
I will be test subject number 1.
This is lead nitrate. Uh-oh.
Oh.
Oh.
I think I know how.
Oh.
That was a dirty beaker. Nobody saw that, right? Except
Except everyone.
and the people on camera. Okay, we'll just do this. Are you ready? Okay, don't miss it. It goes quick.
We could just go replay the video.
3, 2, 1.
Whoa. Can I drink?
Is it drinkable?
Well, I mean, anything's drinkable.
Yeah.
But
Will it be good if I start?
Would it kill me?
Would it kill me if I drink it?
I don't think it's that.
Oh, the better word to say, is it safe to drink?
Drinkable is a better word.
Drinkable?
I'm just having fun with these highlighters.
I don't know. Those are the ones with the orange juice. You might have really
Wait, that would be, this is also
It's
like,
more yellow than orange.
no,
Can't be
imagine if you like,
Okay, number 2.
in which like that wasn't your orange
All right,
juice.
and number
That's yellow juice. That's banana juice.
Bananas don't make juice.
Yeah, they do. I'll make banana juice.
But
I could do it.
make it that yellow.
Food dye. Remember chromatography?
Sure.
All right, so I have some zinc metal here. I'm gonna put in this test tube.
I don't think yellow 46 would do that.
It would.
I know.
Some
They're
mixture.
really hard. They're like
Because I have red.
very irregular
I have the
shapes.
primary color, so I can make any yellow I want.
That yellow.
Oh, I should. Hopefully that was close enough on camera. Okay, so zinc metal. I'm gonna react it with hydrochloric acid, HCl, and then observe what you see. So then after this one, then talk as a table. Once again, what trends or patterns can be used to identify chemical changes from all 3 sides of our triangle. Okay. All right. Hydrochloric acid. This is a 4 molar concentration of HCl.
That's a lot of mold there.
It's pretty strong. I'm gonna spill it on myself.
Oh, oh.
What's it gonna do?
Setting a bad example. Nothing, but it's a bad example, I guess.
It's just soda. That's how they make soda, guys.
That's how they make your Sprite. Especially McDonald's Sprite.
It looks like Sprite. That's all it is. Highlighters are fun.
Okay. Talk to your table, fill those in. What can we see? What can't we see? Ready, go.
What do you see? A change.
A change in state of matter. Because they all change like their state of matter. Like that one turned into gas. The other one also turned into gas. Except that one. That one turned yellow. I'll say most of the time. Chemical structure. Wait, has Lehigh ever won state?
We had high school.
Water.
I don't know. We were second last year. Just to Olympus.
Do you want us to win state this year?
What?
He wants us to win this year.
Hey, girls. Girls.
These girls? No, all of
Your
us.
boys aren't winning. Your boys can't beat Olympus. Or us. Your boys are like our
Our
boys.
boys can beat
Olympus.
Lehigh.
Olympus scored 800 points this year.
Okay, maybe not Olympus. But we can beat you, Chris. Because the only thing standing between us and winning girl side is you guys.
Yeah, your girls are fine. I don't think your boys will.
See, that's the reason why Lone Peak every year wins. Only on the girl side. Because all the good club girls,
They all transferred
they
though.
all transfer. And it's unfair.
It's so dumb. Why didn't like Danny transfer that?
I thought Van lived in the back.
Danny.
Oh, Danny?
short this time.
All that is
Okay, here's what's gonna happen. Ready?
She doesn't like celestial.
That makes sense. That's valid.
We're gonna bring all the ideas together to hopefully get a full picture of what physical versus chemical is from all three sides of our triangle. Okay? Here's how we're gonna do it. I'll give you a second to discuss after I tell you who's. So one person from every table is going to have to share something. Okay, I'll tell you who the chosen person is. Now, when it's your turn to share, you can share what you have, or you're representing your table, so you can also share what someone else has. So that's where, if I'll give you a minute after I tell you who the chosen one is, if you want to talk to your table really quick to get ideas, okay, you can do that. Second thing is you always have the option, instead of sharing like the section I've asked you to share about, you can also ask a question. So if you're like, maybe don't have something, or you're like curious about something in that category of physical or chemical changes, you can ask a question instead. Okay? All right, so the way we're going to determine who the chosen one is today is look at your chemical symbol. Look at your chemical symbol on your desk. Whosever atom has the highest atomic mass, you are the chosen one today.
47, you have the highest atomic mass.
Yeah.
I know, you're a 50-50 chance.
Wait, hold on.
No.
Oh, wait. Which one? What's your atomic mass? 50, dang
Yeah.
it.
Here, you can switch with
No,
So I'm just going to come around and it'll just be like one of them.
keep it over there, because this one has markers, and I have other markers.
Oh.
So as long as you have something in each, then you go.
Dang. That's rough.
Okay, here we go. Ready? All right, starting at this back table, who's our chosen one? Liam? All right, stand up for us, Liam, so people can hear you a little better. Okay, so as we go through this, everybody else, so this is a one person talking at a time situation. So if you're not the chosen one, zip it. Okay, as they're talking, this is where you should add to your own. So if they say something that you don't have, or you're like, ooh, that makes a lot more sense than what I put, right, add to your own thing, okay? All right, Liam, so tell us just for this category, so for physical changes, what do we see with our eyes?
Phase changes.
Love it. Phase change is a huge one, right? Physical changes are all about phase change, liquid to solid, gas to liquid, any direction of phase change, definitely a physical change. Thanks, Liam. Have a smiley face for that. Okay, coming back to the middle of that table, who's our chosen one? Christina. Okay, Christina, can you tell us what can't we see with the physical?
We can see it like the IMF.
Love that. It's all about the IMFs when it comes to a physical change. Intermolecular forces are breaking, but that just makes it a physical thing, right? Particularly with our dissolving salt, right? That's how it dissolves, is because the IMFs interact, pulls the salt crystal apart, and so it's just that. One thing I want to add here, in case you put it, I don't blame them, because when you're younger, like, you gotta like explain things to where people are at, and it's not that you're lying to them. Sometimes it's just they don't understand enough to like understand more. So sometimes when you learn about physical changes in like lower grades, sometimes they emphasize the fact they're reversible and chemical are non-reversible. If that's a definition in your head, get rid of it, because it's false. Some physical changes would be really, really hard to reverse. Some chemical changes, a lot of chemical changes you can reverse. And so don't use reversible, just in case that is something you thought. Don't use it anymore. Okay, Christina, have a smiley face, thank you. Okay, corner back table. I should like, well, I guess I could call you by your family name, but.
Hello.
All right, Bryson. What about writing for a physical change? What are your guys' thoughts on that? Or you can ask a question.
What should I write?
Good question. So if we think of one of the demos, so we had nitrogen gas, right? So nitrogen gas as a symbol would be, we'll learn why it's N2, but it's N2. In this unit, these little symbols are going to be very big players of saying if it's a gas, a liquid, or a solid. Oh, I don't know why I write a G. It wasn't a gas to start with. It was a liquid. So do a little L. I typically do a cursive L, so it doesn't look like a 1. Okay, so we have N2 as a liquid. What did it change into? A gas. So what's its formula? though, is just really the state of it. It's still the same substance in the end. Okay? All right. Questions on physical change before we go through chemical? Okay, come into the table right in front of them. Caleb, for chemical, what are some things we see with our eyes?
They bubble, or like they change color in a way that isn't what you'd expect.
Ooh, love that. So 2 identifications is one, if you see bubbles, that can be a big indicator of color chemical change. You can kind of do bubble / gas, right, if a gas is being emitted. And then unexpected color changing, definitely a good indicator of a chemical change. Thanks, Caleb. Have a smiley face for that. Evan or Garrett, did you have anything else for that same one that they didn't say for chemical change? Yeah. Besides color change or bubbles, did you have anything else? Ooh, so we could put, because dissolving we want to be cautious with, but let's say like new substance, right? Like when the aluminum went away, there's now this red brownish thing, right? So big thing is if you see something new that wasn't there before, right? There's a good chance like a chemical reaction is happening. So good. That was my fish for that, Garrett. Another one I want to add here, if you have it, is temperature changes are a huge indicator of a chemical change, right? If it just gets hot or gets cold on its own, that indicates something is going on more than just your typical phase change. Okay, who's our chosen one? All right, what can't we see with a chemical change? What do you think, Ben?
I said that bonds are being broken and reforming.
Oh my gosh, you took the words right from my brain. It's all about bonds breaking and bonds forming. And we can't see that with our eyes, but that is always what happens when it's a chemical change. Bonds break, bonds form. Now, I often like to think of the elements as Lego pieces, okay? And when they become a molecule, the Legos stack together. And it's so crazy. Like, chemistry is weird because at the molecular level, it can be so simple what's happening. This is going from here to here. But on the practical level to us, it changes it drastically when the Legos unstack in one arrangement and restack in a new one. It changes so much of what it is, right? When it's a physical change, it's the same arrangement the whole time, right? Perfect. How's my face back? Okay, table up front. Who's our chosen one? All right, Scott. What do you think? For writing with a chemical change, what are your thoughts there? Good, I like that. There's like a before and after showing the change. So let's write, we're going to write the chemical equation for this demonstration. Okay, so what I mixed here was we had copper chloride, Cu, which is CuCl2 is its chemical formula. What state was my copper chloride in? Aqueous. Aqueous is what you use for something dissolved in water. Because it wasn't like I melted copper chloride, I just dissolved copper chloride. Okay? So copper chloride was reacting with, what did I react it with? Aluminum. Which was in what state?
Solid.
A solid. Okay? So imagine once again, you have this Lego arrangement of 2 of those and 1 of those stacked together. And then this arrangement of just aluminum as a solid. As it reacts, the aluminum bonds with the chlorine and the copper becomes a solid. So that's what this reddish brown gunk in here is solid copper. Yeah, so if we pulled it out and dried it, we could melt it down into copper. Well, I mean it is copper, but it looks more like copper that you're used to seeing. So what we end up with is something called aluminum chloride, AlCl. Don't worry so much about where these little numbers are coming from. We'll get there. The big picture is recognizing that in a chemical reaction, right, you get a rearrangement of the bonds, right? Bond was broken here, and then a new bond got formed. This one is left out on its own. Yeah, Emily. Oh, no.
No, it didn't. It just has low battery.
Oh, But did it stop? Or did it
No,
still
it's
keep
still
filming?
going.
Can we make it?
I don't know.
power.
You can.
Oh, it's still filming, hopefully. Thank you. We have a lot of people gone today from all across, yeah, because there's a bunch in this and in last grade too. Hopefully it didn't miss that like last 5 minutes. Thank you so much, Emily. Okay, any questions on chemical versus physical? All right, let's write down what we said just in some more words here at the bottom. Oh, hold on here. Okay, so once again, physical changes really are about IMFs, right? Changing the state of it, but the Legos themselves are still the same. Where a chemical change is all about changing the actual bonds themselves. Now moving on, you should be able to identify a chemical versus a physical change. Like if given a description, you should be able to say, oh, that's just a physical change or that's a chemical change. Outside of doing that, we really aren't going to deal with physical changes much more because this is chemistry and so we're focused on chemical changes. So the next thing we're going to look at here with chemical changes is the balanced equation itself and how we read and interpret these plus sign and arrows. Okay, so there's your last blank for identifying chemical. Once again, this right here, this box up there kind of gives you some other things. One we didn't see today is also light, right? Light's another thing. If it makes light on its own, like a glow stick, it's a chemical reaction happening. So that light is coming from that process of breaking bonds. So, okay, all right, questions there? Okay, question for you, and you're gonna move according to how you feel. Okay, now with this, I encourage you to move to where you truly feel. Don't just be influenced by those around you, because you need to be able to justify your choice. Okay, so here's the question. Don't say anything out loud, because you're going to do it to yourself. Okay, so the question is 2H2O and H4O2 the same thing? So yes, no, and be able to justify. So when I say go, if you think no, you're going to head to the window. If you think yes, come to the cupboards. If you're undecided, you can stay in the middle. Ready, set, go. And that's okay. You can stay, if you're like, I'm not totally sure, you can stay in the middle, and then their job is to convince you otherwise. Are you in the middle, Ephraim, or are you kind of that way in the middle? You're that way? Okay, come up here. So you two chat about, okay, so everybody in that huddle of people, find somebody next to you and share with them your justification of why. Ready, go. So share with your thoughts on the why. And then in a second, they'll share and see if they can convince you. Okay. Okay, so our job now is we have two who are undecided. Okay, your job is you're trying to convince them to come to your side. Okay? No, not by bribing them. Okay, Bryson, you want to say something to convince them?
I say we do an experiment. We have them over there drink H2O, but then we also have them drink H4O2 and see if they have.
And if at any time you feel like you want to move, you can. Do you guys feel convinced to come over here or not? No? Okay. I like your proposal though, Bryson. That's my face. Anyone else want to add something? Yeah, Lily. Okay, everyone listen to Lily.
So 2H2O, that's just two like H2O molecules that are just like together. H4O2 means that it's all one bonded molecule, which is not the same as 2H2O. Because like if you think about the picture in your brain, they're gonna be different because the H4O2 is gonna have the two O's in the middle and then the H's around it, and that's just not the same thing as 2H2O molecule.
Okay, thank you. That has my face. Are we convinced one way or the other yet?
Yeah.
logic over here? What was our thoughts? Why did we say they are the same? Okay, everyone listen here.
I said yes, because the formula works like H2O and 2 before this formula. It means you 2 multiplied by 2 and 2 multiplied by 4.
Yeah, which is totally logical, right? If you use the rule of distribution, as you learn in math, right? You distribute that 2, it seems to be the same. This is once again a great example where chemistry is crazy. Because mathematically, they seem like they're the same.
Yeah, but I cannot understand why
Chemically, they're not though. Have a smiley face, you two though. I'm proud of you for being brave with your thoughts. And you guys also get a smiley face for getting it right. Okay, find your CDN.
See, I was doing exactly the same, but I wasn't
Okay, so we have this law in science, in the world, where scientists have determined that matter, or mass, cannot be created, and it can't be destroyed. Okay, atoms are simply rearranged. So the atoms that exist now in the world have existed since the beginning of time. They just have been rearranged into something else. So the atoms inside of you right now, once upon a time, could have been the atoms inside of a dinosaur. Who knows, right? They decomposed into the ground, and then that went into some food that your mom then ate, and then came into you, right? It's possible. Okay. It's, to me, it's kind of like this law has been around for a long time in our understanding. But it is interesting to think about, like, once upon a time, they didn't believe this. They literally believed that matter could be destroyed, right? That, like, if you burned something, that it was gone. But we now know if I burn a pile of wood, are the atoms of the wood destroyed? No, they're just converted and float away, right? But they're all here, it's just rearranging, right? So with this idea and a chemical reaction, so once again, this right here is a chemical reaction, okay? Chemical reactions are like a mathematical equation, but you do have to be cautious of truly looking at it just like a mathematical equation. First off, this is like an equal sign, but the direction of it is significant in what's actually happening, right? So this is indicating the change and the direction of the change. This is changing into this. Now, that doesn't mean it can't go backwards, but under these conditions, it's only going that way, okay? A plus sign, right, indicates that these two things are just mixed together, right? Their Legos aren't stacked. They're just mixed together as it's been made, okay? Now, with this chemical reaction, right, we have the molecules themselves, right? Water, hydrogen, oxygen. Then you also have numbers that are indicating this idea of it must be balanced. The number of hydrogens on the left must equal the number of hydrogens on the right, because things can't just come from nothing and they can't just be destroyed. So that's our next objective today, is learning how to balance a chemical equation. Now, some of you may have already learned this if you took chemistry last year, or sometimes you're introduced to it even in like 8th grade science. They kind of introduce this concept. I ask that if you have learned it before, that you still stay with me, because some of the equations we do might be a little harder than what you've seen before, and I just have a few tricks that can help you. The concept isn't different, how you balance, but it might help you out with some of the harder ones we look at. Gavin?
Wait, you said it says it can't be created, right? Matter?
Yeah.
How is there matter if it can't be created?
Deep question. So that is something there's various theories about where matter has come from, and you have to decide for yourself of which theory you want to believe. Yep. Because there's not one universal agreed upon thing of this is where matter came from. Big Bang is the idea behind it, right? The Big Bang is like a proven fact. But how the Big Bang happened is a little bit unknown. So yeah, good question though, Gavin. Okay, let's define a few vocab words here. Okay, so when I look at a balanced equation, we have something known as the subscript and something known as the coefficient. Now this is where, once again, if you want to use different colors and actually just like highlight the word subscript and then color those numbers the same way, you could do that, or draw arrows, whatever. Okay, so when I look at a balanced equation, the subscript are the small numbers, so I'm going to do them in purple. These are my subscripts. Think sub, right, they're below. The subscripts are the small numbers in the compound formula. Okay? The coefficient is the large number in front. So kind of vocabulary, just to understand. Subscript is the small numbers. Coefficients are the big numbers. Now, anyone have an idea, if I raise a hand, if I change a subscript, what happens? Anyone, if I raise a hand, have an idea?
Will it change the coefficient?
Yes, Bryson?
Will it change the coefficient?
It doesn't have to.
Will there
It
be
could.
more of it?
Something bigger, though, would happen. Alex?
The molecule will change, like the
You change the identity, right? Which is exactly like your hypothetical way to solve our problem, is that H4O2, the subscripts indicate what it is. It's not the same thing as water. It doesn't actually even exist. There's no such molecule as H4O2. But they're not the same thing when you change a subscript. So that's the first thing to recognize, is when we learn to balance today, you can never change subscripts, because then you're changing the recipe completely. Okay? But if I change a coefficient, what does that change? Zachary?
The amount of molecules?
Yeah, just the amount, right? The number of sets in it. Just like in our picture here, right? There's two waters, but they are separate from each other. They're not chemically bonded. Okay? All right, now this is the recipe, right? If I want to make hydrogen and oxygen from water, this is the recipe of what I need. I need 2 of these to make a ratio of 2 to 1. Now, with a recipe, what's really crazy about chemistry, once again, is like in cooking, like you have to be, in baking, you have to be very particular about your ratios. Otherwise, you'll mess up your cake, right? If you add too many eggs or not enough flour, like the cake won't turn out how it should. But in chemistry, you can just, are we at 10%? Yep. We can do this. Come on, phone, don't die on me. So in chemistry, you can actually just throw together whatever ratio you want, and it will react just as it did here. But in the end, you might have what are called leftovers or excess. Stuff that didn't react, but it doesn't prevent the reaction from happening. It would be like in cooking, you could just throw together flour, eggs, sugar, throw it in, it'll give you a cake, and then you have a pile of all your leftover ingredients that didn't get used. Right? That's what happens in a chemical reaction. So keep that in mind, that the recipe isn't what I have to use. It is how it's going to react, though. Right? It's always going to react in that ratio. Okay? All right. Now, in balancing, I'm going to show you 2 different methods you can use. Here's the steps to write down, so as we go through these, you have something to come back to. With these methods I'm going to show you for balancing, though, it really doesn't matter what you do as long as you get there. I'm just going to show you some different ways you can think about it if you've never learned this before. In the end, this is one of those things, if you can balance in your head, you don't have to show work. So you don't have to show work for balancing. My one word of caution, because I have seen this happen before, if you're balancing in your head and you keep getting them wrong, don't balance in your head. Just write it out on paper. There's nothing wrong. There's nothing to be ashamed of it. I write it out on paper 90% of the time. I have too much in my head to keep track of things in there. But once again, I'll show you 2 methods that you can use to kind of help you think through the process. But the main goal is whatever's on the left must equal whatever on the right. They have to be the same. Okay? All right. Does everyone have these down if I go to the next one? method, this is a very visual method, so if you're a very visual person, this one tends to be the one that students like to do. Okay? Whether or not you like this, I would encourage you to write both methods down, but if you get stuck later, you have something to come back to and use. Okay, so for this method, I want you to grab from your box, let's do green, orange, pink, and blue. Grab green, orange, pink, and blue with me. Okay?
I do.
All right, what we're going to do is, in a sense, we're going to draw out the reaction to see how many's on the left, how many's on the right. So we have a different color for each atom. When you balance, you have to balance down to the atom. Okay? All right, so I'm going to let's make our aluminum pink. So I'm going to draw a pink circle for my Al. I'm doing them big so you can see it. You can literally just do like a dot. You don't have to even draw a circle. Okay? Now on this side of the arrow, so the arrow is the balance. On this side of the arrow are 2 aluminums. Okay? Now notice I've drawn those 2 dots connected because they're bonded that way. Okay, don't draw them as like 2 separate things. Okay, all right, Cl I'm going to make orange. So I'm going to draw 3 Cl's connected to my 1 Al because the molecule is AlCl3. Okay, coming over here, finding my Cl, I just have one of them in that compound. So let's add 1 orange dot. Okay, switching colors again. Let's do green for our sodium. We have 2 NAs and 1 Na. And then do your dots for your sulfur. So 1 sulfur here. 3 sulfurs there. Okay, everyone got their colors drawn? So this is something like you can do this on your homework, you can use colors. Some students, like when they would do it on a test, if they like this method, they'd actually just would pick different shapes, right? If they just had their pencils, they'd say like, let's make this one a triangle, that one a square, that one a circle, that one a star. You can do it that way too, okay? The idea of this is this one's really nice because you just look at it and we can see, all right, start with 1 at a time. When you balance, fix 1 at a time. Don't try to fix all the problems at once. So I see 1 pink is on this side, but there's 2 on that side. So I need to have had 2 of these to start with. So I'm going to add another one here. But keep in mind, this is coming in a group. So in order for there to be another Al, there also had to have been 3 more Cl's. Right? These little caterpillars come in groups. You can't just add 1 random atom. Okay? All right, pink, fixed. Let's go on to orange. So I now have 6 oranges on the left. So I'm going to need 6 oranges on the right. Now these ones come in a set of 1. So I'm going to need add 4, 5, 6. And just like before, if those are getting added, then the sodiums are coming with it. So I fixed my pinks, fixed my orange. I'm just going down the row. Let's fix green. So I have how many greens on the right? 6, so I'm going to need 6 total here. These come in sets of 2. The nice thing is with balancing is if you focus on 1 at a time, the last one should just take care of itself, which the blue did. I don't have to do anything with the blues. Okay? So we now add coefficients to represent how many of each is needed for it to be balanced. So for this to be balanced, I need 2 of these molecules. I need 3 of those molecules. 1 of those and 6 of those. Now, just FYI, it's not necessary to put 1s. You can, there's nothing wrong with it, but it's like writing 1x. Right? You don't have to do that in math. But if you want to put it because you don't want to just have nothing there, you can put the 1. So, okay, questions so far on balancing? What it is, why we're doing it. Okay, let's do another one, and this one I'm going to show you a non-colorful way that you can also keep track if you would like. I call this my scoreboard method. Okay, so you only need your pencil for this one. Not quite as pretty, but gets the job done. So with the scoreboard method, you're going to make a score underneath the arrow of everything that you need to keep track of all the individual elements. Okay, so I need aluminum, I need copper, and I need chlorine. So every individual element you put down on a list to keep score. Okay, then you take what is the initial score. So on the left side right now I have 1 AL, I have 1 CU, and I have 2 CLs. Okay, so I'm just writing just like before, you got to get the initial count. Going to the other side, I have 1 AL, 1 CU, and 3 CLs. Okay? Now, just like before, pick one. In this case, there's really only one to focus on because the others are already balanced. So keep in mind, this is the scoreboard. This is the game. You play the game and then update the score. Meaning, I need the score to be equal. Right now, it's a 2 and a 3. So what would be the least common multiplier? 6, right? So I'm going to play the game. So I want CL to be 6. So what do I need to put here for it to be 6? So I put a 3 here, so I played the game. Then I change the score. Now, in putting a coefficient, it influences everything with it. So it is also going to change the score of CU. Okay? But that's fine. We're focused on CL right now. We'll come back to that later. Okay, so coming over here, we want the score to be 6. So what do I need to put in the game? A 2. So that changes to 6. It also changes the score of AL. So we fixed one, messed up some others. So let's fix those. So AL has a score of 2 on this side. So to make the score equal, I need to put a 2 there. CU is 3 on this side. So put 3 here. And now we're balanced. Questions on that? Once again, the biggest mistake I see students make when they're doing this method is changing the score and then playing the game. And it gets you really messed up because they start thinking that since there's a 6 here, you should be writing 6s somewhere up there. But that has nothing to do with it because it's just about the total amount. Okay, we're going to do one more together and then we'll try some for some smiley faces. Any questions so far? Okay, let's try this one. That is a little trickier and brings in some, I'll give you some hints you can use that make balancing go faster when things get more complicated. I'm going to use the scoreboard method again. That's my preferred way, but once again, if you prefer to do the colors, there's nothing wrong with that. Whatever gets you the right answer is the best method for you. Okay? All right, now, 2 hints with this one. So as I'm making my scoreboard here, so I need to put hydrogen on my list. Okay? You can group things together on your scoreboard. By doing that, it simplifies how much you have to count, and it will make it go a lot faster. The way you know you can group something is because it is a group on both sides of the arrow. Polyatomic ions are what they are. So, for example, SO4 is a group. On this case, there's a group of 3 of them. On this side, it's still a group. It just doesn't have parentheses because there's only one of them. But instead of counting out sulfur and oxygen separately, I can just count it as the group on my scoreboard. Or in a sense, if I was going to use colors, that would count as just one color. I wouldn't have to do a sulfur color and 4 oxygen colors. So it makes it go a lot faster with counting when you group. Okay? All right, so I have H, I have SO4 I'm going to group. I need Al. Now we have OH, which is a group on this side. Is there a corresponding group on the other side though? No. So then you can't group it, so I'm going to have to separate out O and, oh, we already have H in our list up there, but H separately. Yeah, Garrett.
Could you like write it now to just O3, H3, or does that change those?
In a sense, that's what we're doing. So yeah, if it helped you to like think about it, it's obviously something different. But if it helped you remember that you have 3 O's and 3 H's, that would be, yeah, I think it should work out fine. Good question. Okay, now the second thing that can be really tricky with a balanced equation is what's going on with our hydrogen here. On the left side of our arrow, we have hydrogen in 2 locations on the same side. So when you're keeping track of your total, you've got to count all the H's on the left. So my total H's is 2 and 3, so total of 5. Let me see that.
Why is it 2 and 3?
Because it's everything on the left, right? So let me change my color here. Yeah, so 2 from there and 3 from there. Okay, sulfur or sulfate, I just have one of them. Aluminum, I just have one, and oxygen would be at 3. Going to the other side of my equation, I just have 2 H's, I have 3 SO4s, I have 2 aluminums, and I have 1 oxygen. Okay, so that's my initial one. Once again, because we're grouping it, that saves us from having to like add up the oxygen separately and combine them. Okay, I'm gonna not worry about hydrogen. When you have something that is in lots of places, just let it take care of itself at the end. If you try to fix it first, you can get in this loop of like, it just isn't ever working for you. So let's skip that and go to the next one. So SO4, I need to play the game so the score is the same. So up here, I'm gonna add a 3. Okay, that changes this count to 3 now. But now we have to update our total hydrogen count. So that gives me 6 hydrogens here, plus the 3 over there, so that gives me 9. Once again, that's where it can get a little messy, is when you have things in lots of places. You just gotta keep track of them. Okay, we fixed our SO4. Let's fix our aluminum. So I need it to be equal. So I want this score to be 2, so I'm gonna come up here to make it 2. I wanna put a 2 on that line. That fixes my aluminum to 2. Changes my oxygen to 6, and my hydrogen total count to 12. There's 6 and 6. Okay? All right. Coming down, let's fix our oxygen. So I have 6 on this side, so I want the score to be 6 on that side. So if I put a 6 here, that will fix that. And oh, look. Hydrogen's got fixed too. And we're done. Questions? It is like balancing, it's like a problem-solving thing. The more you do it, the better and faster you'll get at it. But there are some like tricks and stuff that can make it easier. But any questions before I have you try some for some smileys? All right, turn the page. There's 3 problems on the next page. Let's try them out for 3 smileys. Ready, set, go. doesn't matter where you start.
You're not being pessimistic or being realistic.
Okay, are we ready to check these three? Does anyone want another minute? Yeah, another minute. Okay, give me your focus back up here, everybody. Let's check it, and then we have one last thing we're going to talk about before we end today. Okay? So, answers should be going just on the blanks across. So you get a smiley face for each one you bounce correctly, so up to 3. So you should have 2, 2, 3 as your coefficients. You should have 2, 1, 2, 1, and 2, 3, 2, 3. Questions on balancing, how it works, how to do it?
You get 3 smiley faces?
Yes, so 3 smiley faces if you got them all right. Okay, now I love how a lot of you are proactive where you get something done early, you start on your homework. Great, but put it away because there's one last thing we need to talk about. That's same topic, but a little different that I don't want you to miss. Okay, so come back to your notes with me, everybody.
Okay.
So the next thing we're going to look at here, and it will bleed into next time as well, but with this idea of balancing is, like I mentioned, that a chemical reaction is the recipe. It tells you, in order for this to work perfectly, you need 2 of these for every one of those, and it will make 2 of these. Okay? But in actuality, you can mix whatever you want. So the next thing is take